today we're going to talk about the final numerical method technique, and it's completely new. So far the numerical techniques we've done, we sort of met before at GCSE, but we're talking today about the Newton-Rhapson method. Forgive me for consulting my notes to confirm I'm spelling it right. And the Newton-Rhapson method, it's really important you remember it is used to solve equations equal to zero. Where does this equation equal to zero? So it may be that we would be required to do a bit of rearrangement first to get it to that state. We've already done that with sign change, haven't we? So we're used to doing that sort of thing. So let's say we've got some function and we want to know when it equals zero, and we sketch it. And we sketch it and it looks like that. So we've clearly got a root here, a place where the graph equals zero, but we don't have the algebraic techniques up our sleeve to work out what that value is. And so what Newton-Rhapson does, which I consider to be absolute genius, it says this, right, it says pick a point. We're used to doing that. And at that point, draw a tangent to the curve. And work out where that tangent crosses the x-axis, and make that your next point. And then, at that point, draw a tangent to the curve, make that your next point. And hopefully you can see how, before long, in this particular circumstance, you are going to get the root. So x0, x1, x2. Because if your value of x is actually at the root, then you are already on the x-axis. So if we're asking where does this graph intersect the x-axis, well, we're already there. So this does a really clever thing. It says, let's take an x value, and then let's work out this distance here, and subtract that from my first x value to get my second x value, and then let's work out this distance here, etc., etc., etc. So let's just take this part of the diagram on its own and see if we can work out some distances in the situation. So this is my x0, and I want to know what this distance here is, because my next value is going to be at this point here. I use the gradient to do this. The gradient of that line is the gap that I'm after. So I don't know what I'm going to call that. I'll call that question mark. That's the thing I'm trying to work out. This area that I've shaded green here. And this distance here is the value of my function at x0. So it's f of x0. Except I'm going to, we're going to be using this technique not just at x0 and x1, but at any value. So let's change it. And so the gradient is this height here, which is the value of the function at that value of x, divided by my missing distance. Now, I don't know the gradient of the tangent, or do I? Do I know the gradient of the tangent? How do I work out the gradient of the tangent to a curve at a particular point?
Take the derivative.
I differentiate, yeah. So the gradient of this blue line is the same as the gradient of the curve at that point there. And I work out the gradient of the curve by differentiating it and substituting in the value of x. So that is actually f dash of that value of x. So the gap, how far I need to move to get to my next x value, if I rearrange that formula, is that. So I start at x0, and then that calculation tells me how far I move back to get to x1, and then that calculation would tell me how far I move back to get to x2, etc., etc., etc. Let's turn to the formula sheets, because the actual formal version of that is stated on the formula sheets. So let's see what it says in the formula sheet and see if we can relate it to what we've just calculated. So, do I need... If you need help with this, I will come now. That missing that. So, Newton-Rhapson we will find on page 7. Most things are on 6 and 7. And it says if you want to solve f of x is 0, you use this iterative method where your next value of x is your current value of x minus this calculation. So what they're saying is to get the next value of x, you take your current value of x and you take away the gap. That calculation is the calculation we've just used to calculate the gap. So if the first 5 minutes of this lesson has been completely meaningless to you, it doesn't matter because the formula is on the formula book, in the formula book. However, I like us to have some idea about where it comes from. So this calculation here is basically saying how far you need to slide along the axis, and of course that may be a negative value, in which case we'd be sliding this way along the axis. Now the choice of value is always given to you, and that may be as a result of a sign change calculation, or it might just be that it gives you. But you know, you can maybe see how in some situations the choice is really, really important. So let's start. Let's look at a separate sort of graph. Let's look at a good old-fashioned quadratic. Let me give you just a second to think about where would be a really unwise place, and where would be a really unwise place to start with your x value? I'm just going to give people a chance just to think about it. Where would be a really unwise place? We're trying to find either there or there. Where would be a really unwise place to start? What do you think, Harrison?
That side of the graph.
This side of the graph? So let's say. Do you mean over here? Say.
Yeah.
Let's try it. Let's stretch. So if we start maybe here, and we go up to there, draw a tangent at that point. This seems okay. Seems okay, doesn't it? What do you think?
You can do it right in the middle.
When you say right in the middle, do you
Like
mean?
at the bottom of the parabola.
Ah, right. Yeah. This is the only. It's Newton-Rhapson is a lot more forgiving in terms of your initial choice. Although some values take a long time to get there, but there is one place that you really shouldn't start, and that is at a turning point. So if I used a value of x there, the curve is there, a tangent to the curve at that point never touches the x-axis. So that really, in terms of choice of value, the only thing you need to remember, and in the few questions that's cropped up, it's always been in there, why is it really unwise to start at x is minus 3? And x is minus 3 just happens to be where there's a turning point. So Newton-Rhapson works pretty well apart from if you happen to start at a turning point on the curve. That isn't going to work. So Newton-Rhapson, the one value you shouldn't use is a turning point. And if you've got a graph with several turning points, then that would be unwise. Let's get the books out and let's have a look at some examples of this, because it really isn't that complicated, but it's just about getting used. Actually, I might have to ask you to show me. So we are on page 283. We'll do the worked example together, and then we'll so 283, we've got example 6 on page 283, I thought we wanted together, and then I'll get you to do some individual on the board. Sorry, not 286. 283, example 6. 283, example 6. There we go. Okay, so we've got a function, and we're trying to solve when does that function equal 0. So big ticks so far in terms of suitability for Newton-Rhapson. They tell us there's a turning point on our function when x is p. Why is p not suitable for first approximation? Because it's a turning point. Newton-Rhapson wouldn't work. So instead, we'll skip straight to part b, and we'll use x0 equals 2. So my proposal would be in a question like this, because we're going to be doing a lot of f of x and a lot of f dash of x, I'm going to write those two things down. So my original function is this, and to differentiate that, well, familiar with that. And so my first value is 2. So my second value will be 2, the current value of x, minus 2 substituted into the original function, which I'm just going to write as f of 2, divided by 2 substituted into that, which I'm going to write as f dash of 2. And I'm going to do this not using the answer function, but using 2 arrow x. So I'm going to put 2 arrow x, and then I'm going to type in this 2 minus blah 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 divided by blah 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 blah. Press equals, and that will give me my next value, my x1, and then I will go up and is it better to do the answer button maybe? So to do the answer button, then you've got to type it in once, haven't you? Yeah, I lied. I'm going to use the answer button. So I'm not going to do 2 arrow x, I'm going to do 2 equals. So 2 is the answer button. And then I'm going to type in 2 minus answer cubed plus 2 answer squared minus 5 answer minus 4 over 3 answer squared plus 4 answer minus 5. Yeah, that's going to be easier, isn't it? So let's see if you can do that. Are you calculated up? And just see, what does it say? It says apply it twice. Apply it twice. So they've done, they haven't asked us to do the sign change, but they've indicated that there's a value, a solution somewhere between 1.8 and 1.9. So this is just for the other max. So 2 equals, and then I did the Newton-Raphson calculation, 2 minus f of 2 over f dash of 2, just using the answer button, gave me 1.86 recurring. I then pressed equals again, and that gave me, now I didn't need to type anything again because I'd used the answer button, and that's as far as the question wants me to go. So now it's getting me to use sign change. So it says, we think this is now, even with only 2 iterations of Newton-Raphson, this is the answer to 3 decimal places. And let's test it using an appropriate interval. So this is error interval question, isn't it? So what we now need to do is we now need to do f of 1.8555 and f of 1.8565 and show that there's a sign change in between there. That, remember, is of the original equation. So we're doing that, not that. Okay? So we're doing that in the original equation. So if you just double check that that does give you what you're after, and then I am proposing that we spend a bit of time just working through page 184, starting at question 2. So the exercise on page 184, we start at question 2 and just spend a little bit of time going through that. I'd like to finish the lesson by talking about a couple of more real-worldy practical examples, but yeah, have a go at that. So I've done, I've differentiated it. I left it as x to the minus 2 rather than writing it as 4 over x squared. Either is fine, but I then did minus 0.4 equals, so that's now my answer value, and I typed in answer minus answer squared, blah, blah, blah. And this is going to give me my answer. Minus 0.3258. And that was all the question asked for. Let's just see how much they want it to. 3 decimal places. And that was it, not even a sign change there, just straight into. So, you know, it's pretty straightforward. The only tricky question about choice of value will almost certainly relate to a turning point. Yeah, questions when that crops up. So we'll just spend a little bit more time and then we'll perhaps look at one of these practical questions. So choice of value, well, yeah, we've seen a couple of times now this question about explain why it's not a suitable value, and you know, it's the turning point, definitely not suitable. Close to a turning point as well, I guess really we could perhaps expand. So for example, this diagram shows it quite nicely that x0 in this example isn't at a turning point, but it's close to a turning point. So the next value would be here, and where does that meet the curve? That's up there somewhere, so it's going to come back. So, you know, it will get there eventually, but close to a turning point is never a good choice as well. And that's why Newton-Raphson is nearly always combined with sign change to get a pretty good idea of where you're looking to start with. If you've got a good idea about where you're looking, then it works really, really quickly, as we've shown. Now, those questions are you know, they are bound to have more complicated functions because that's the whole essence of numerical methods. They're used to solve things that we can't solve algebraically. So, you know, you're not going to get quadratics because we can solve quadratics using other methods. But ones like that, and that's why I'm not doing my job if we don't look at some really quite scary looking functions, and one of those we'll find on page, I think it's 288, question 4. Yes, 288, question 4. And Max, I'm sorry, there's no way you're going to see that, so I suggest hopefully you've got a copy of the book. 288, question 4. Sorry, I don't mean you. I mean that Max on the right. This question gets you to solve a problem using both iteration and Newton-Rhapson. We'll just do the Newton-Rhapson bit. So we don't need to do this whole bit here. We can start with our h of t and differentiate it, and then we're told to use 8 as our first approximation in the Newton-Rhapson. It looks a bit nasty. Let's just double check that we're okay with one of the terms. If I start you off with the sine term. So we know when we differentiate sine, we get cos. So sine of t would become cos of t when we differentiate. And we know sine of something like 2t becomes cos of 2t multiplied by what you get when you differentiate the brackets. Here we've got sine of t over 10. I'm going to write that as 1/10 of t. And you know, we can put it in a bracket, doesn't really make much difference. So that's going to become the cos of 1/10 of t multiplied by 1/10. And you know, it may be easier to leave that as t over 10 as long as you're happy that the two ways are exactly the same. And obviously, a coefficient out the front passes through unchanged. 40 times 2, that would be 80. 40 times 1/10, that would be 4. So differentiating that term becomes that. I'm hoping you can perhaps use a similar approach to differentiate that term, and then have a go. So we're not doing A and B. We're not doing the iteration part of it. We're just using h of t, which is instead of f of x, h dash of t, which is instead of f dash of x, and we're just doing Newton-Rhapson once with 8 as our first approximation. I suppose if you're only doing it once, you don't really need to use the answer button, do you? But